can see this kind of mistake from the year 3 student. If you were to find the percentage in error, most of the students have no issue in finding the difference, right? You all know that, okay, if I want to find the error, of course, we need to find the difference. But when you ask them to calculate the percentage error, they tend to not too sure what actually to put. For example, difference over they're not sure whether you find the difference over the actual value or the difference over the apparent value. That should not happen already because you are year 3 already. I think even this kind of mistake, it should not happen to a SPM student as well. Okay, if you were to find the difference or percentage error, is always to divide it by the actual value, right? The original value, basically the nominal value, what we call. All right, so systematic error, basically, just now we have mentioned. Okay, this error actually they will consistently appearing in the display of the. If let's say you what you call, if let's say you were collecting data from a screen display, so usually if let's say you have a systematic error, it will consistently appear there. Okay, you will consistently have that. Okay, for example, if you were to measure your own weight, right? If let's say if you use those mechanical weight, right, where you can actually like tune the you can actually tune the value one. So if let's say the value is not being on the weight itself is not being calibrated properly, it is already showing some value. For example, it is already pointing 2 kg before you even stand on it, right? If let's say you are 40 kg, you stand on it, it will always give you 42. If you are 60, it will give you 62. So this one will consistently appear in your result. Okay, so this type of error usually you can break it into 2 different categories. One is because due to the instrument, right? You did not do your calibration or maintenance properly, and sometimes it could be due to environmental error. Okay, so like when you go to a different altitude, right? You go to the mountain or what, maybe it's affected by the pressure, right? So this one is affected by the environmental error. Okay, so this is what we say, this is what we mentioned just now. When you have a limitation, you should be able to provide a suggestion on how to improve it, right? So limit in your report or any report that you're going to do, your thesis or your FYP, your capstone, you should always have this limitation, and sometimes we call limitation and future work. Sometimes we call it future work. So in this future work, you provide suggestion on how to overcome the limitation. So one of the example, okay, it could be like this. So if let's say we were talking about, oh, we have instrumental error when we collect the data. So how are you going to improve that, right? So you can say, okay, we should select a suitable instrument, or we should apply correction factors, and also to do some calibration of the instrument against a standard, right? You should be able to provide a suggestion for your limitation. Okay, so statistical analysis, I think the important part of this we already covered, which is the child-awareness criterion. Okay, but of course, all this mean I expect you already know lah. So we are not going to discuss here how to calculate mean. Okay, so deviation of the mean, this one will help you with your child-awareness criterion, right? If you still remember how to actually do the calculation for child-awareness criterion, right? So this one, so I want to randomly ask in case some of you forget. Sean, are you there? Sean,
Yes,
can you tell me when the question asks you to use bias basis to analyze to to perform some statistical analysis, right? If let's say I want you to use bias basis to calculate the standard deviation, you should use the population standard deviation formula or sample.
What station of fire? What?
Bias, never, I write it here. So if let's say the question asks you to use bias basis, perform your statistical analysis using bias basis. So when you want to calculate your standard deviation, which of these formula is the one that you should choose?
Population standard deviation.
Confirm ah?
Confirm.
Okay, correct. You tikam one or you really remember?
Tikam, tikam.
Tikam. Eh, 50% chance, although 50% chance to get it right is quite high, but 50% chance to go wrong is also quite high, you know. Okay, so remember well before you go to exam, don't tikam in the exam.
Okay, okay.
Okay, so probable error. Okay, although we do not have question on probable error, but I think it's actually a interesting error. It's actually an interesting method that you all can use. Okay, because sometimes you all may ask, right? You all may ask this kind of question. When you are taking measurement and your measurement are in increment of 0.01, how do you know whether your increment is appropriate? Have you all ever actually thought of that? No, right? You all just randomly like put 10, 20, 30, suka hati one, right? So if you ever really think of that, this one can actually help you to resolve your doubt, right? When you if you were taking measurement, you are taking 0.01, right? Then 0.02, so something like that, right? How do you know whether this is appropriate or not? Why don't you just take a bigger one, 0.1? So probable error can help you to determine that size, whether it is appropriate or not. Okay, so if you look at this, your probable error will define the middle 50% of your normal distribution. All right, this is a normal distribution curve, right? Usually, this probable error is counted by this 0.6745 standard deviation. So if you look at the deviation, if 0.6745 define 50% of the error here, right? So it will be from, basically it will take 50% of the normal distribution. So how you actually want to calculate it, you can, first, of course, you must know what is your standard deviation. Okay, and then you check your data, whether most of your value actually fall in between the 50% or not, right? If not, then you can actually reconsider your size of increment when you want to collect the data. If let's say you're interested to know more about this probable error, I actually have put this. I think this reference is quite good. It actually, this article, okay, it's up to you want to refer or not, but I put it here in case you want to use it. This is actually quite a good explanation. It's quite detailed. They explain to you how you can actually determine the size of increment by using the idea of probable error. Okay. All right. So child-weighted criterion, I think we already discussed about it, and we also have done some past year or question, something like that. I think I gave you before to do it in the class. Okay. So if let's say you really want me to explain again on how to use this table, please let me know. All right. So another simple statistical method that we're going to use here is this student T distribution. Why I say simple? Because I believe all of you here have took this subject called, I think, statistics, right? So in your year 2, you learn different kind of method there. One of them is actually student t distribution, right? And then you have independent t test. You have you have dependent t test or something like that, right? But in our subject here, uh, the idea is so much more simpler lah. So we just do a very simple student t distribution. We don't have those like independent t test or dependent t test, and then you are given different sets of data to compare them. No. So our method here is just a very simple one. Okay, basically you only need this formula to perform the calculation for example like tolerance limit, or sometimes the question will sometimes the question will reverse engineering a little bit and ask you to find the value of t. Okay, so don't worry, this formula of tolerance limit is provided in the exam, but of course you need to know how to do the basic calculation. Okay, so t, I think everybody knows what is this t value already. Okay, so n here is the number of samples, and you must be wondering, or I'm not sure whether you all can recall or not, this degree of freedom. Okay, degree of freedom is basically your numbers of sample minus one, because take note of this, because when you read from the table, you need this value, degree of freedom. Okay, so else you will read the wrong line. Okay, so look at this. If let's say your n equals to 10, then v equals to 9. So you must read from here. I think the common mistake that I see from students is that they always overlook this degree of freedom. Then end up there, if let's say n equals to 10, they will end up taking value from this line instead. Then of course, you will not get it right. Okay. Another question that I would like to test, you know, some of you, because you have learned about statistics before. Okay, that is a very important question to test whether you really understand the topic or not, right? Why do I say so? Because that day when I teach the year one student on, it's a math subject, so we were talking about this RMS, like how to calculate the RMS value. I think all of you have learned this before also, right? Because you have learned some electrical subject. So I asked the student, especially the EE one, because they should be very familiar with this. So I asked them, what is this IMS value for? Why are we looking for the IMS? You all know how to calculate IMS, but what is it for? What is it for? Right? So same thing I want to ask you. Since you have learned about this statistic in your I think it's last semester. You all learn about what? 95% confidence level, 90% confidence level, 80% confidence level. What does it mean? Random. Wilbur, can you tell me what do you understand about this? Like when we call 80%, 90%, 95%, what is the purpose of using the what it actually means lah, basically? If let's say I have 95%, I'm 95% confidence level. So what does this mean? Okay, if let's say I have 20 data here lah. So if let's say I said I'm 95%, this test is performed with a 95% confidence level. So what it means? Wait, it's okay, take your time. You just literally read what I have down there, is it? Okay, so basically, if some of you notice that I've added some extra lines at the bottom, right? So when it comes to 95% confidence, so means that you have 5% of chance being wrong, right? So if let's say 90% confidence interval, it means you have 10% chance of being wrong. So some I'm not sure some since you are doing capstone, you probably will read a lot of these papers. If you see those data, most of the time you will see the comment down there one. Like this test is performed at what confidence level. Okay, if let's say I were to submit a paper to a journal now, okay, and then let's say I perform a certain test, then I conclude, okay, this is a 90% confidence level, right? That the result is significant. Sometimes the reviewer may ask, why is it so low? Why is it not 95? Okay, so basically, this where this amount of the percent of the confidence interval is how confident you are with the data, like how many percent of chances that you are being wrong with the significance of the data of the result. Okay, all right, so let's go back to our calculation here. Okay, so what kind of question can come up? um Usually it's very direct. You just need this one formula. Okay, so your tolerance limit equals to t, uh, I think t multiplied with, okay, standard deviation divided by square root n. So if you read the question tells you that the mean is 15, right? And then your standard deviation is plus minus 0.1. So the question asks you to determine the tolerance limit at 5% significance level and also 1% significance level. Sometimes the question that will be rephrased in a different way. So in this case, when they talk about this, determine the 5% significant levels, they are actually asking you to find the tolerance limit at 95%. Okay, so you have this n equals to 10 because you have 10 observation. Okay, so 10 observation, your degree of freedom is 9. So if you refer to the table, degree of freedom is 9, 95%, right? So you will get 2.262. So you get your t value here already. And then you have your standard deviation. You also have your value of n, which is 10. So you can calculate your tolerance limit from there. Okay, so another one is just a repetitive one, so I will leave it to you. Okay, so this is a little bit of reverse engineering a little bit. Okay, so the question asks you to get the estimate for the number of measurement needed. Okay, if let's say you have a precision of 0.5, this one tells you the standard deviation. You are also given that the tolerance limit is 0.02. Okay, so what will be the number of measurement, right? So if you look at this formula, okay, you will end up with this t equals to 0.4 square root n. But what will be the appropriate number of this n? If you are doing calculation, right, this is the calculated one based on this formula. If you look at the table, 5% level of significance, this will be the value if you refer back to the table. So from here, right? When it is at 95, right? So if you refer here, so you bring back to the to this page. This is from the table. This will be the calculated one. So how do you decide? I think this one actually goes back to your theory that you have learned in your statistic, if not mistaken. How do you decide? So if let's say I have N 25, 26, 27, which one should be the one that should be the one you choose? I give you 3 minutes to recap back the theory that you have learned in your statistic. Later I will random pick one of you to justify why. I'm not sure you can remember or not, but this is something you have learned in your statistic. But the theory, I'm not sure you all can still recap or not. I just give you a extra elaboration from here. Okay. Um, in the exam, right? Sometimes when we reach to this point, right, students tend to choose 26, but the actual answer is 28, 27. This is the actual answer. But students tend to choose 26. From your point of view, if you forget about all those theory from your statistic, yes, you will end up choosing 26. Why? Because logically you will think that, oh, if I have a calculated theoretical value here, and this one is from the table, I should find the lowest difference between them, which is in this case, the difference is only 0.02, right? This is what usually student will think. And the difference between this is that 0.022. So student will think 26 is a better answer for this case because the difference between them are the lowest. Can anybody tell why we end up with 27? This one is actually your statistic class one. Xiaoyan, do you want to try? Xiaoyan, any idea if you still remember your something you learned from your statistic? Why instead of 26, logically everyone will think it's 26 because the difference is the most minimal one, right? But why the actual answer is 27? No, no, forget already. Hey, your statistic lecturer is Dr. Cole, is it? Okay, never mind. Okay, I think you forget already. But I will not go into the theory because this is not statistics class. So, statistically, your calculated value must be higher than your table value. This is the theory. But if you ask me how they derive this theory, I can honestly tell you that is not my expertise already. Okay, but statistically, uh, your calculated t value need to be higher than the value that you get from the table. So that is why 27 is the correct answer. But in the past year exam, even when student give me 26, I actually still give correct lah. But it's actually not so correct. By right, it should be 27. But I understand from student point of view, they probably already forget about all the statistic theory, and this is not a statistic paper lah. So based on like logic reasoning, we always say we find the closest one, right? Like closest one. So even student write 26, I also give marks up. But I just want to point it out to you statistically from a statistic theory point of view, your calculated value need to be higher than the one you get from the table. Okay, so that is why we get 27. Okay, I hope everybody can follow. Sometimes I feel like online class is a little bit risky because I cannot see your face, so I'm not sure you get or not. Then I will just keep talking from my side. So if you think I'm going a little too fast, please stop me. Okay. All right. All this confidence level. Let me see any question that I want to bring up to discuss with you. All these are quite direct ones, so I think I will just let you do it. Okay. I think this part. I think for this. I think you also should know already, if let's say you were to find a certain value, if let's say you have t equals to 2.53, right? Then I want to ask you, what is the confidence level, right? Then you have to do a little bit of interpolation if let's say you cannot find it from the table. So in this case, this is n equals to 10, v equals to 9. Okay, so same line here. If let's say your value is 2.53, that will be in between here, right? So what is the confidence level? You need to do some interpolation to find. Okay, so this is a bit like you just trace back the values, but it's not stated here. But you know it must be between these two, right? Because you have n equals to 10, v equals to 9, and your t value is 2.53. So you know it's between 95 and 98. The confidence level is between this. Then you have to do some interpolation. Okay, so this one I'm confident that you all know how to find. Okay, so I don't go into detail with that. All right, I give you a 10 minutes short break because later on we have a very important things to learn, which is something to do with max one. So I want you to go and get some fresh air and make sure you come back with a fresh mind because you will learn about max later. This one is just a revision I do for you because this is a very important technique to be used in uncertainty analysis. So I give you a short break of 10 minutes. Yeah, short break of 10 minutes. Okay, 10 minutes pass. Uh, before we go to the, oh my god, I hope you cannot hear the knocking sound from my neighbor. They've been doing renovation since forever. All right. Okay, so I just quickly go through this limiting error lah. Okay, so before we go to the uncertainty analysis, okay. Basically these limits are the sometimes we will call guarantee error as well. Okay, sometimes we call limiting error. Okay, so for example, usually this kind of value will be specified in the what you call that. You know when you buy a certain things like the equipment or what they come with the manual, is it or something like that, right? They will tell you what's the limiting error. Okay, for example, if let's say a resistor, you buy a resistor lah. Okay, you buy a resistor. Hey, hold on, my pen. Turn on my pen first. Okay, so if let's say you buy a resistor, right? If let's say you want to buy a 500, maybe a 500 kilo ohm or what lah, right? But sometimes there will be some range. Not necessarily when you use this, it will give you the exact 500 kilo ohm, right? So, but then if you read the manual, they will usually they will try to play safe. They will say, oh, this is a plus minus 10%. So it means that the resistance will fall between 450 and 550 kilo ohm. Okay, so they cannot they basically just promise you the error will not be out of this range. So basically the error will be, they can only guarantee you, okay, it's 450 between 550. That's it, right? So of course, if let's say you have something that is come with a higher accuracy one, you definitely have a smaller or lesser limiting error. Okay, no question on this, but just to give you some idea what is this limiting error is. Okay, now we will move on to a very, very important part of this subject. One of the important part of this subject, which is this uncertainty analysis. Okay, last sem I have 25%. I allocate like 2 sub question. One is 10 marks, one is 15 marks, if I remember correctly, for this uncertainty analysis itself. This year one, you will see when you sit for the exam. Okay. All right. So why do we use uncertainty analysis? Okay, basically we want to quantify the quality of the result. Okay, sometimes if let's say I ask you whether this accurate or not, if you say, oh, quite accurate, low accurate, or high accurate, but this is just this is only verbally, or what you call it, qualitatively, you're explaining, right? You just explain, you just qualitatively describe that, but you did not quantify it, right? Quantify, this is okay, you did not quantify it. So the purpose of using this uncertainty analysis, okay, we do not just want qualitative analysis, we want a quantitative. Okay, same, this is something that I would like to advise all of you here as well. When you do your report, or when you do your capstone, when you do a FYP, you are engineering student, try to focus more, or try to do more of this quantitative analysis. Okay, do not just describe your result without giving, without quantifying it or give a value to that. You are supposed to use the numbers to prove it or to describe the result. Okay, so basically that's the purpose of uncertainty analysis. If I ask you to describe the quality of the result, uncertainty analysis will help you to quantify, to give a value. So basically, during this process, we will quantify and combine all the error. Okay, because errors are only effects, but uncertainties will help you to quantify it. Quantify it. So by giving numbers. All right. So before we go into the concept of this uncertainty analysis, I must at least give you a revision on partial differentiation because you will use a lot of partial differentiation, okay, in this uncertainty analysis. Some of you actually already go through this before. I'm not sure about because quite a lot of you are from diploma, but I'm sure you learn about this. Just that I'm not sure in which subject. But for those who take year one, they learn it in their year one sem 2 apply engineering maths. Okay, they learn this in their year one sem 2. If you have took this subject in your year one sem 2 apply engineering maths, basically this is the same slides. I think I will also provide these slides later lah, for your reference. But if let's say you want to use reference book, it's also fine one. It doesn't matter. Okay, unless just in case some of you lazy to find reference book, then I just upload these slides for your purpose. Okay, it's the same slides when you take the applied engineering maths. Okay. So don't think you have escaped from your year one sem 2, then you no longer use this. So now is the time for you to apply what you have learned in the past. Okay, the idea of partial differentiation is actually very simple. Okay, you can just ignore this. I just give you the idea. If let's say you have a function, right, with three variables, x, y, z. Okay, and then I ask you to find the partial derivative. Okay, that will be del f, del x, del f, del y, del f, del z. Just to be more precise, this is not d, right? D is differentiation. Del is what we use when we do partial differentiation. This one you can read it as del, right? This is how you write del. So when you do partial differentiation, the idea of this is very simple. If let's say I ask you to find del f del x, okay, means that you see all the other variables here, y and z, as just treat them like a constant. Treat them like constant. Okay, so same thing. If let's say I ask you to find del f del y, you must treat all the other variable, which is x and z, as constant. Okay, remember this. So repeat the same for the del f del z. So let's go through example. So this is a max class from now onwards. This is to help you with the uncertainty analysis. Okay, I give you example. Okay, so obtain the partial derivative f sub x. This one is a different form. This one, if you are lazy, you can write it as f sub x. If you're hardworking enough, just write it as del f del x. It's the same thing. Okay. This one means del f del y. It's up to you, whichever way you want to write it. It's just different form. Okay. Okay, look at first question here. If let's say you have a function contain these two variables, x and y, okay, this one is not multiplication, please. This one is just to tells you the function contain these two variables x and y. Okay, so f equals to xy squared plus 3x to the power of 3. Now I want you to find del f del x and del f del y. Okay, so how do you do it? So you can do it like this, or you can write it as del f del x. So when you want to do a partial differentiation with respect to x, you treat your y as a constant. Treat this as constant. Okay, so we go terms by terms. Go to the first term first. You treat y as a constant. So if you differentiate x with respect to x, you get 1. But y is a constant, so you just copy it back. That's why you have y squared. Okay, so you look at the second term. Okay, this one no y, so you can just directly do your differentiation there, which is 9x squared. Okay, so I repeat another example when we have del f del y. So in this case, you treat x as constant. Okay, so you treat x as a constant, then you differentiate y with respect to y. You get 2y. So x is a constant, you just copy that back. How about this 3x to the power of 3? This one is a constant standalone, right? It's a standalone. Imagine when you have y equals to 2x plus 3. I ask you to find dy dx. You know 2x will get you 2, but if let's say you have a constant, this will become 0, right? So 2 plus 0. So same thing, it's the same situation here. If let's say you have a constant standalone now, which is this 3x to the power of 3, you will get 0. So this is how you perform partial differentiation. You just have to remember this important concept in your mind. When you were doing partial differentiation with a certain variables, treat the other variables as a constant. Okay? I just go through a few more examples to make sure you are familiar with this. Okay? Don't worry. I know you must be wondering, are we going to have those very complicated function, then you forget the formula? No, you won't have. Most of the time, you only have polynomial. Most of the time, right, you only have polynomial. Okay, you won't even get sine. So far, we never even test student on sine or inverse tangent. So usually the question are quite direct. Usually are polynomial function. Okay, because this is not a mathematic test. Okay, so how about this? I'll give you another example here. And also bear in mind, you will not have higher order partial derivative. We only need to do first order partial derivative. Higher order means when you have to do a few more times of this partial differentiation. So we do not have that. So far we only have first order. Okay, for your uncertainty analysis. Okay, so I give you another example on how we do it. This is important. This is important, but I do not have. Wait. I find an appropriate one for you to learn. Okay, I think this is quite a good one. Okay, if let's say you have a function r with these three variable x, y, z, right, equals to this square root x squared plus y squared plus z squared. Okay, so if I ask you to find r sub x, or what we call del r del x, means that in this case, you must treat your y and z as a constant, right? Treat these two as a constant, y and z as constant. So how do you do the differentiation here? If you still remember, you can actually write it as x squared plus y squared plus z squared to the power of 1 over 2, right? So if let's say you were to differentiate this with respect to x, bring down the 1 over 2, right? And then copy the whole thing. And then minus 1 from the power. So 1 over 2 minus 1, you will get negative 1 over 2. But is that all? No. Because based on chain rule, if you forget about this very important rule in your differentiation, okay, this is chain, you have to apply chain rule, right? Okay, so based on chain rule, you actually still have to do something with your function there. That's not the end. Okay, so you have to continue to do your differentiation with respect to x. In this case, if let's say y squared stand alone, z squared stand alone, you only left with x squared. So differentiate x with respect to x, you get 2x. So that's how you get the final answer here. Okay, I think you're, I feel like some of you maybe already blur here because you forget about all these chain rule or product rule and what else? Another one is the product rule, chain rule, and there's another one rule. Forgot the name. I think someone typed there. I can hear some. Eh, what sound did I hear? Do you all remember? There's this.
Caution rule, is it?
Yes. Very good. Caution rule, correct. Boy. I've been teaching this. I cannot recall. Sorry. Caution rule, correct. All these you all must know. Basic. Okay. So what we did just now is chain rule. Okay. You have to keep doing your differentiation until there's no function left for you to do the differentiation. Okay. I think I want to give you all more revision on this partial differentiation. Else you cannot do the uncertainty analysis. You will stuck there. So I need to give you a few more example already. Okay, so how about that's it. So short one. Oh, okay. Never mind. I can give you the question. So same thing. If let's say I ask you to find r sub y. Not bad, Xuan. Your memory is very good. Quotient also you can remember. Okay, so r sub y here, or you can write it as del r del y. So same thing. Bring down your power and then x squared plus y squared plus z squared minus 1 from the power that will be negative 1 over 2. Okay, but that's not the end because you still have a function here, right? If let's say you were differentiating this with respect to y, x is a constant and now it is a standalone constant, so lucky you do not have to do anything about it. So you left with only y squared. So differentiate y squared, you get 2y. Okay, I want to test your understanding. Okay, if let's say I change the question now, if let's say I have let's say I have x here. Never mind. I change the color first. If let's say I add x here, and then I add another x square here. Okay, I want you to tell me what is the R sub x for this case. I give you 1 minute to think about this, all of you. Okay, I changed the question a little bit to test your understanding. Right, and I want you to find the R sub y as well. R sub z as well. Then I give you more minutes now. I give you 5 minutes. Okay, we are supposed to have 3 hours class today, so I try to give you some break in between so you can rest a little bit. But okay, so if you cannot tahan already, you tell me to stop. Okay. So I give you 5 minutes to do this. Okay, so not sure whether you are still behind the screen or not. Jen Hong,
Yes, miss.
yes, Jen Hong, can you give me the solution for this R sub x?
Okay, we see.
Yeah, you can just verbally tell me. I will just write it I will write here.
Uh,
Mm. Never mind, just write wrong also never mind. Okay, but first lah, of course, r 1 over 2 because you have the square root, and then you copy the whole thing, x square plus x square y square plus xz square, and then negative 1 over 2. But then how to continue here?
和概念总结
Sorry?
前面不
Huh?
Oh, nothing to. Multiple.
Where's Jen Hong? Why Jen Hong disappear already? Okay, Jen Hong disappear already. Never mind. I asked another person. Chun Mei, can you continue from here, Chun Mei?
Yes.
Chun Mei,
4x.
continue from here. 4x? 4x? Did you say 4x?
Uh-huh.
Mm?
Is it 4x, 2x plus 2x?
4x plus 2x?
2x plus 2x.
2x plus 2x?
That's all.
That's all?
Yeah.
Okay, why you treat it as a constant? So if you differentiate x squared, you get 2x is correct. But now your constant is not a standalone constant. It is attached to this. It is in a relationship with x squared. So you cannot leave it alone. So you must copy back your y squared there. So imagine you treat it like a numbers. If let's say this is 4, you will not leave it alone, right? You will 4 2x, isn't it? So it's the same thing. So unless this is a constant standalone, then you can just forget about it. Okay, so just now I've changed the question here. So this one x squared, this one x, right? So it's not the end yet. You still have, if you differentiate x, you get 1. And then you have your constant z squared there. So plus z squared. Okay, good that I call you all to test your understanding. Okay, means that you all are still not familiar with this. Never mind. Do more revision on this. Okay, do more revision on this. Okay, so anyone disagree with the answer here? No, should be fine. So let
No miss, no
me.
miss.
Jen Hong, where did you go?
Just now, Mike got problem. I rejoined the meeting.
Mike got problem.
So now
Your-
I will do the second one.
Oh, okay, nice. Okay. Oh, nice, Jen Hong. I thought you want to run away. Okay, very nice of you. Volunteer to do the RY. So, okay, Jen Hong, can you give me the R
Yes,
sub
miss.
Y? Yeah.
How I 1/2 multiply
Wait.
x square plus x square y square plus
Yes.
xz square,
Yes.
and then power -1/2.
Yeah,
Then
correct.
multiply
Multiply with
x square
x square.
plus x square 2y x square
X square plus 2yx square.
plus xz square.
Okay, so what is wrong here is that because now you are doing differentiation with respect to y, so you must treat x and z as a constant.
Oh,
So this is a constant standalone, so this should be 0.
0. Okay, okay.
Yes, but this is
Then the
correct.
x square also 0.
Yes, correct. This is 0, correct. So
Okay, okay.
you all can understand better now?
Yes,
Never
miss.
mind. I test another student for the third one to make sure you really understand what I've been discussing.
Yes, we did.
Why? Why you want to bully him? Is he not here?
Huh?
He's
He is
sleeping, is it?
watching TikTok.
Huh?
He is watching TikTok in his room.
Oh. Let me see. 这是谁呼啊？维健，维健
Yes, miss.
啊，维健 come. Third one for you. R sub Z.
Okay, okay. Basically, the previous equation will be the same. Only the
Oh.
the behind one will be some
Okay.
different.
Can you tell me what's the things that difference here? Okay.
And then have to times two x z only.
You sure?
Of course.
Not bad. Correct. Oh. Okay, so this is correct. Okay, so this is all revision from your year 1 max. So if you really forget everything already, please do more revision and exercise on the partial differentiation. Okay, because without partial differentiation you cannot go carry on with the uncertainty analysis. So let's see any question here we can do more, or I will just find question for you. Okay, I think we don't need chain rule. We no chain rule. So I think I will just find more question for you to do. Hold on. Just to test you. Get ready. Okay, so I will give you the question. Okay, if let's say I have this. Okay, I give you this function equals to C A. This is actually past year paper, okay? And then I have this bracket 2P1 RT1, and then I have this differential pressure, okay, and then 1/2. Okay, nice. Which one is a constant? Let me see. Okay, R is a constant, so don't need to do anything, right? R is a constant here. So I want you to give me this del F del C give me what is this del F del A. Why? I think, let me check the attendance. I think I have. Eh, I have 18 of you here. Which means I have 3 students gone missing. Never mind, I will take my attendance later. Okay, you do this while I'll take your attendance. So del F del P1. Can you do it now? Okay. Because test yourself. This is literally what is coming out last semester. Okay. So del F del differential pressure del test yourself. Okay, test yourself whether you understand the partial differentiation topic or not. Okay, I give you a longer time to do this. I give you 10 minutes. Okay, to test your partial differentiation knowledge. I give you 10 minutes. I will guide you later. Don't worry if you do not know how to do, I will guide you, okay? I just want you to at least try. I give you 10 minutes to do this one first. By the way, there are different ways to do this. You can use chain rule. You can also separate the variable out and yeah, I give you hint already. Separate the variable out and do the differentiation accordingly. There are different ways to do it, but you will get the same answer, don't worry. Okay, I will take your attendance. So when I call your name, you say you just say yes lah. Okay, so okay, Amelia, I saw him already. Kai Xian.
Yes.
Okay, Xiao Yuan or Xiao Yuan, I call him already. Zhen Qian, I saw him. Qi Yuan, Xian Tai.
Yes, miss.
Okay, Zhun Ming, I just call him. Kenneth appear here. Zhikang.
Yes. Hello.
Okay, I can hear you. Eng Hu, Eng Kui.
Yes. Yes.
Okay, Chai Huat.
Yes, miss.
Just now Eng Hu sounds very sleepy. Later I will ask him to solve this. Jen Ho already did. Yi Hen. Okay, Yi Hen gone missing. Wei Jen, I just call him. Sean, I just call him. Zhong Zhe.
Yes.
Ki Cheng.
Yes, miss.
Okay, Zhijian. Zhijian not here. Zhijian, Yi Hen not here. Wilbur. Okay, Wilbur, I just call him also. Nit Hong.
Yes, miss.
Weird. I have 19. Who suddenly joined? Suddenly got extra student come in because I want to take attendance, is it? Okay, so Zhijian and Yihen not here today. Any idea where these two go? Or they just don't know. I'm not sure. Because Zhijian macam first time skip this class. Okay, now my 10 minutes. Okay, I already give you hint on the different methods, so try and do it now. This is last semester, 2024-01 semester. Means this one is a June paper. Okay, if let's say I give you 10 minutes, that will be 4:50 already. But I think I should give you a 10-minute short break as well because else it will be too long for you. So we will continue the discussion at. Should I give you a longer break? Do you all need a longer break? Or you're fine? Because you're comfortably sitting there. You're okay? If I put 4, will it be too early? I give you including a short minutes, a short 10 minutes break for you. So we will come back at 4 p.m. to discuss this. Okay, I include the 10-minute short break for you. All right. Enghu just now? Enghu, tell me what's the partial derivative for this P1? Enghu, where are you?
Yes.
Yes, give me the solution for this.
Solution. The final answer.
Yeah, I can.
C CA times what difference P? Let's go what
CA multiplied with what?
the triangle P
The okay. And then
over over RT1 square root.
the whole thing square.
No, behind the RT
Like this.
and no, this this one already done. The square is at the below only.
Hmm.
The behind the RT only.
Okay, wait. Let me. Never mind. So C A, and then you have this. Just now you give me.
Triangle P.
Oh, okay. And then your square is only for this. Do you mean this?
And no, got one more. That's down the square root not at here. Got one
Oh, the
more.
square root not here.
Behind got one more.
Okay.
One over the question bracket one.
Oh, wow, why so complicated? Never mind. Never mind. The bracket one so mean is 2 RT1 differential and then 1 over 2, is it?
Negative 1 over 2.
Oh, negative 1 over 2. Negative 1 over 2. That's all for your answer, is it?
Yes.
Wow. Let me see. Let me see. It's very far from the correct answer. Never mind. I will guide you. Okay. So yeah, you can tell your mic already. Is it? Thank you. Thank you very much for sharing your answer. So okay, so after today, I think you all have to really brush up your partial differentiation. Okay, so look at this. If let's say now I have to do differentiation with respect to this P1. Okay, so you treat all the other variable as a constant, right? So constant, and then I already forget who answered just now. Oh, but never mind. I did. What? Wait, who? I think your answer is not entirely wrong. I think you just haven't rearranged. Okay, never mind. Never mind. I think I did not go into detail in your solution, but I think if you rearrange, it's not entirely wrong. But never mind. So what you can do is okay. So 1 over 2, right? And then you copy this entire thing here to P1 RT RT1. Okay, the RT1. So we have RT1 here, and then the differential pressure, then negative 1 over 2, and then you have to do something with what is inside there, which is 2 over RT1 with the differential pressure. So if you read, wait, this is the same with what you gave me just now, right? I think I did not look into detail. Sorry. It's my fault. Sorry. Okay, so if we rearrange this, you will get let me rearrange this. So you will get 1 over 2. See, I feel like something is missing. 1 over 2. Oh, okay, no. So if I rearrange this, I will get 1 over 2 CA bracket. So this one now. Okay, if let's say you have rearrange, I rearrange. So you will get 1 over 2 because negative 1 over 2 plus 1. Right. So, and then you left with P1 negative 1 over 2. Okay. Eng Hu, I forgot your answer already, but I think what you did wasn't wrong. But I just that I didn't look into your look into details. Sorry. So, can you check if your answer is same with mine after I rearrange everything? Is it the same? Is it the same?
Oh, I still got P1
Hmm?
at the behind one.
Hey. Yeah. Sorry. Good that you realize. Sorry. Hey, I rearranged wrongly already. So here is only 2. Okay. Is it the same?
Mhm.
Is it the same with yours?
But the final the P1 the final bracket is P1 is what?
The P1 is here, right? P1 should be to the power of 1 over 2. Negative 1 over 2. Different.
Oh,
Yes?
don't know.
Huh?
Different.
Which one is different from yours?
The middle bracket is same with the question bracket, but got negative 1 over 2, and
You have,
the
you have
final
negative 1 over 2 here, you mean?
I arrange one.
It cannot be because here is negative 1 over 2, but here is 1. So if let's say you have A negative 1 over 2 multiply with A, you will get you should add them, right? Negative 1 over 2 plus 1. So this one equals to A 1 over 2.
Oh, then I do wrong.
Can the rest of you if you I double check my answer also the rest of you. Okay, sometimes I may copy wrongly. Okay, so yeah, I think maybe your rearrangement you have done something weird there, but never mind. There's another method. I have seen students do that, which is what they did was instead of using chain rule, they just separate everything out, right? So from here, what they did was they just separate everything. So here you have 2, and this differential RT1, and then they just separate it out first. It's still the same thing. Haven't Haven't do anything yet one. So what they did was del F del P1. So all these are constant, right? So just copy them back. You can have different method to do it. It's not wrong as long as if it doesn't go against the theory. So if you differentiate P1 here, you will get 1 over 2 P1 negative 1 over 2. And then, yeah. So it's the same thing, actually. Whichever method you all think is easy. Okay. So what I did was I used chain rule. But this one, the student, very smart. He just separate all the other variables out first. Then only he do something with the variables. I hope everyone can follow up to now. Okay. So I move on to the next one. Okay. So next one will be so next one will be del F del this differential pressure. I think I should ask Kenneth. Right, Kenneth, we have this online class for you. So yeah, in return, you must do your friend a favor. Kenneth, where are you? Where is Kenneth? Kenneth, where are you? Oh, Kenneth disappeared already here. We all had this, we all are having this online class because of him, but he went missing. Text him, bring him out. We had this online class because of him, but he went missing. How could he do that? I can't see these two others are who because I think limited place, but Kenneth, where are you? 6, 12, 14, 4, 16, 18. One of you gone missing. He's not here. Oh yeah. Tell him to come back, else I don't give him attendance. Okay, so we continue from del F del this triangle here is the basically is the differential pressure. So one means that you treat all the others as constant. So continue from here. CA to P1 RT1 means so I will have this. If let's say I do chain rule, okay, so that will be 1 over 2 P1, copy the whole thing back, RT1 negative 1 over 2, and then I have to differentiate what is inside there, so I will left with 2P1 RT1. Okay, if I rearrange the whole thing, I will get 1 over 2 CA. Process the square root with the other one, I will left with 2P1 RT1 1 over 2, and then differential pressure to the power of negative 1 over 2. Anyone get different answer from me? This is by using the chain rule method. But if let's say you are quick-witted enough, you can just do like what the other student did. You will get back the same thing, which is by separating all the variables here from the beginning, right? CA, you have 2P1 RT1 1 over 2, and then you just separate it, and then you just process it separately, right? So if let's say you want to look for del F, del differential pressure here, you will get all these are constant, right? All these are constant, and then you just do your differentiation for this part only. So 1 over 2 del this differential pressure negative 1 over 2, okay, and then 1. So you will get the same thing. Whichever method you find it easier for you, okay, you can just do it your own way, as long as you can see these two are same answer. Okay, if you rearrange everything, they are the same answer. Doesn't matter you use chain rule or you just separate the variable out before you do the differentiation, you will get the same answer. Okay. Let me see again. Why where is he? Have you all asked him? How dare he disappear out of nowhere from the class? Okay, last one. I don't know you all can still tahan or not, because 2.5 hours already. I was thinking to brief you some concept of uncertainty analysis, but I think this partial differentiation probably you already banged on already. Okay, so del F del T1, haha. So this one, should I call name or I do it myself? I do it myself. Okay, so other than this, all the others are constant. So C, A, right? And then 1 over 2, copy the entire thing. T1, and then this one, negative 1 over 2, and then multiply with, if let's say 1 over T1 will give you negative 1 over T1 square, right? Can because this is 1 over T. If you differentiate this, okay, I make it simpler for you. If let's say we have 1 over y over 1 over x, dy dx will give you negative 1 over x squared. Okay, so rearrange the whole thing. You will be getting negative 1 over 2 CA, and then, hey, you all really don't want to correct me when I did something wrong. I have something missing there. Let me ask if you all spot anything that is missing from there. Why you all so quiet one? Jikang, come. Jikang. What is missing here, Jikang?
Yes.
Jikang, what is missing from my solution here? Why you sigh so loud? What is missing from my solution here? Something is missing there. I make a very careless mistake. What is missing there? Something is missing there.
The 2p over r.
Yes, correct. Very good. This is the constant. When I differentiate this function here, inner function here, I forgot. I only differentiate this T1. I forgot that my other constant. Okay, so very good that Zhikang realized that. Okay, so negative, if you rearrange, you will get negative 1 over 2 CA and 2P1 over R, and then T1 negative 3 over 2. Oh, finally. Okay, so anyone get different answer from me? Okay, another way, I show you another way to do this. This is what I did. I use chain rule. Okay, I did not separate all the variables out. So I show you an easier way. Okay, I've seen this student did this last time. So what he did was he just separate everything out again. So you have this 2p1 r del p1 over 2, and then he separate this 1 over t1, 1 over 2 here. It's the same thing. So del f del t1, you just copy. Okay, this is all constants, so just copy them, no issue, copy them back, and then you differentiate this part, right? You will get 1 over 2, and then 1 over t1 negative 3 over 2. Wait, wait. You will get yeah, correct. So, and then this one you will get 1 over t square negative. Okay, why I make it so complicated? Can be very direct, right? Sorry. This one should be. This one you can just directly do it as this one you can just directly do it as t1 negative 1 over 2, right? So you can just directly get your t negative 1 over 2 t negative 3 over 2. Simple. To make my life hard. Okay, so this is what you should get. You will get the same answer, so don't worry about that. Okay, so now it's actually already 4:30. For me, I don't mind to continue with this uncertainty analysis, but I don't know you all are okay or not. If you cannot, then you let me know if you want to stop here. Else, I will just continue. If you want to continue next week, then I will just continue next week. So far we are quite on track, so don't worry about. We are not lagging behind. Don't worry. So, any comment from the floor? Continue.
Miss, can you show just now the final answer? Sorry.
The final answer. I scared I delete already. Oh my god, where is it? I did not. I hope I did not erase it. My goodness, where is it? Here. Oh, okay, here.
Thank you, Miss.
Okay, so Kai Xian, since you have 1 over 2 don't. Okay, typo. Okay, so Kai Xian, how should we continue? Do you think you can still cope with something more today?
If simple one can
Simple one. For me, it's simple because I have been teaching for many years, but I don't know is it simple for you or not. You done copy this already?
Yes.
Yes. Okay, I just give you an overview. So if you all feel like you can absorb, then we can continue. If you cannot, then you just stop me. Okay, then I continue. Okay, so all right. So when it comes to this uncertainty analysis, okay. So if let's say we have zero order uncertainty, take note now, this is only apply for zero order uncertainty. Okay, when we have zero order uncertainty, this is defined by half the resolution from the instrument. Fixed already one. If question asks you what is the zero order uncertainty, it is always half the resolution. Okay, so this is the first thing. And another thing is what we call the instrument uncertainty. Okay, this is something you can find in the sometimes it's in the statement, or sometimes statement as in like this. Okay, so if let's say you have the statement, you buy something, buy some instrument, then they tell you, okay, what is the resolution? What is the linearity error? What is a hysteresis error? Okay, this is in the statement given to you. Okay, this instrument uncertainty is by combining all the instrument error. Okay, and there's this one very important technique that we are using in this uncertainty analysis is what we call RSS method, root sum square. What it means is you sum up all the squares and then you square root it. Okay, you will see that we keep using this RS again and again and again and again for the entire uncertainty analysis. So this is what we call root sum square. Don't worry, later you will see how we use it. Okay. So when it comes to design stage uncertainty, okay, design stage is when you are still at a very early stage. You do not have much information. Okay, so it is only serve as a guide for you to select equipment. Okay, we never use this to report the result because this is design stage. Okay, you have limited information. Okay, we don't use it to report result, but probably serve as a like a prelim guide for you to select a equipment. Okay, basically design stage it is made up of these two uncertainty. One of them is zero order uncertainty. Another one is what we call instrument uncertainty. Okay, so what do you observe from here? This is actually RSS, root sum square. You see or not? So basically, if let's say you have zero order uncertainty, which is the U naught here, okay, so just U naught square. Your instrument uncertainty is UC, so UC square. Sum them up and then square root. This is what we call root sum square method. Okay, root sum square. So this is how you find your design stage uncertainty. Okay, so here is still quite an easy one because you did not really touch the partial differentiation yet. That one I will keep it for next week when we do for the when we do uncertainty analysis for error propagation. That's where you will need more of this partial differentiation. So let's just go to the design stage first. Okay, look at this question. Okay, considering you can read on your own. So considering the force measuring instrument is described by this data. Okay, the question actually asks you to find the design stage uncertainty. So just now we have mentioned that your design stage uncertainty consists of two different uncertainty. One will be zero order uncertainty, and this is already well defined. Zero order uncertainty is well defined by a random called Hong. So what is this zero order uncertainty? It is always defined by what? Hong, are you there?
Yes, Miss.
Yes, zero order uncertainty is defined by what? It is well defined already one. When it comes to zero order uncertainty, it is always half the
The resolution.
yes, very good. It is always half the resolution. So you go back to this page. It is always half the resolution. Okay. So second one will be the instrument uncertainty. Okay, first figure out, if let's say my question asks you to find design stage uncertainty, what should cross your mind? You need to know you have to find the zero order uncertainty and the instrument uncertainty. Okay, first, zero order uncertainty is defined by the resolution, right? Half the resolution. So you know that your U naught equals to 1 over 2, 0.25. So in this case, this is 0.125. Okay, first one. Second one will be our instrument uncertainty. In this case, you actually have two uncertainties for instrument uncertainty, which is one is 0.2, right? Linearity error. Another one is 0.3. So you must be asking, how do we combine this for the instrument uncertainty? Use the RSS method. So your instrument uncertainty will be square root of the sum of this 0.2 square plus 0.3 square, which will give you 0.36. You are done sorting these two, zero order uncertainty done, instrument uncertainty done. So how to find the design stage uncertainty? Basically, you perform root mean square again. So root sum square method. So square root of the sum of zero order uncertainty square plus instrument uncertainty square. That's how you find your design stage uncertainty. Okay, so I don't think I don't think we should continue further with this error propagation. Else you're confused. But at least today you must understand how to find the design stage uncertainty. Okay, we haven't really go into the very core part of doing uncertainty analysis because I don't think you can cope already. So at least you must know today we learn about this design stage uncertainty. Okay, and then it consists of these two, zero order uncertainty and instrument uncertainty. And another important technique is RSS method, root sum square. Okay, so I do a summary of what everything we have learned today. So today, at the very beginning of the class today, we at the very beginning of the class today, we go through some summary on the Wheatstone Bridge. Second, we go through some basic concept involved in measurement error and also some statistical analysis, right? So you have learned about this tolerance limit, right? Tolerance limit, and which is the student t-test. And all the other simple one like find the average lah, range of error, all those are just concept lah, okay, basic concept lah. So child-awareness criterion is something that we already learned in the past. Okay, today we just I just simply go through ask you what is the bias basis and unbiased basis. Okay, it's just some simple revision for you. Okay, and very important one for today is the partial differentiation. Please today go back do revision on this before you go to next class. Else next class when we discuss the uncertainty analysis, you will be blur all the way until the entire day end. So please, next week when you come back, make sure you know how to do partial differentiation already. Okay, so the last part will be design stage uncertainty. Okay, design stage uncertainty. So this make up of two parts, which is zero order uncertainty and instrument uncertainty. Okay, so that's all for today. Okay, today we cover quite a lot of things, so I hope you really go back and sort it out if you still cannot. Okay, and yeah, last but not least, Qi Yuan, remember next Wednesday. Okay, remind me the day before, else I forget. Okay, so I think that's all for yeah, yes, Qi Yuan.
Nothing.
Remind me.
Just
Yeah,
carry on.
remind me.
Okay. Okay.
Remind me on Tuesday. Remind me on
Tuesday.
Tuesday.
No problem.
You just Google check me. I will see one. So I think today we can end our class here because if I continue further, I think you all will. I think your either you bang out or you start to sleep there already. And this is Jen Hong. When I end the class, you're super happy one. Okay, so that's all for today class. Ask Kenneth where is he. Ask him to tell me where is he. Okay, so that's all for today class. So thank you and see you next Thursday.
Okay, thank you, Miss.
Okay.
Thank you, Miss.
Okay, sure. See you next week.